Hi, Mike here, and this is video 2 on central limit theorem. So video 1 is a graphical video on the central limit theorem, and now this is a little bit more of the theory. And we started with the basic idea of when we use the central limit theorem, or why we're using it, and that's to do estimation. And the idea is population to sample the population. There's a population of interest, it has population parameters. We don't know what they are. They exist, we don't know what they are. We collect data, we get guesses, and we want to figure out how good our guesses are, be able to infer back from the sample to the population. So right here in inference, you need some probability to understand inference. Once we do inference, we can get into confidence intervals and then eventually regression. We can talk about relating variables to one another. A lot of good stuff once we understand inference. So again, they're population quantities, p and mu. Sometimes we use pi for the population proportion. We're going to use p, but occasionally you'll just see all Greek letters for population values, and pi with the population proportion. They're unknown. We don't know what they are. There's a true value. They're fixed, but we don't know what their value is. We collect data. P hat is a guess of p, and x bar is a guess of mu. And what we want to know right now is how good are these guesses. So the general setup, of course, is there's a population of interest. You have, I messed that up. There's a population of interest. Then there's a true but unknown value. You collect the sample data with random selection. You get x bar. That's your guess. And then you want to figure out, how good a guess is it? How close is x bar to mu? That's the idea of inference. As an example, we'll show you some data that is done on a regular basis. So the U.S. government has a survey that they run, and they want to figure out the average income of families. And so there's a population mean mu, and they want to figure out the mean income of all U.S. households. And they administer this to 250,000 randomly selected households each month. It's a rather big survey that they do, called the American Community Survey. You can read about it here. They send a lot out, and how do you use the data, blah, blah, blah. You can read about it. And in 2009, the mean annual household income was estimated to be x bar is this. Now, they could claim that mu equals this, but they might be wrong. Because this is only based on a sample. This is the population of all households in the US. And the idea is there's sampling variability. If they collect another random sample of households, they might get a different value. If they collect another random sample of households, they might get a different value again. Every time they collect the data, they might get a different x bar. And the bottom line of this is that x bar is a random variable. It's a freaky idea, but x bar depends on the data we collect. And we can think about big x bar and little x bar. Big x bar says, I'm going to collect data and form the sample mean. It's before we did it. Little x bar is the actual value. We might call that the realized value. But big x bar is random. It depends on what data we get. And because it's random, we can talk about the shape of the distribution of x bar. We can talk about the mean of x bar. We can talk about the variance of x bar. Sounds very bizarre, and it's a thought experiment if anything else. In general, we do this once, and we get a single value of x bar. We can think about, what if we did it over and over again? How variable would x bar be? And that's what we're talking about. So the main idea is that x bar can be thought of as a random variable, has a probability distribution then, it has an expected value, and it has a variance. So the thought experiment, or the theoretical idea, is that you're taking a sample 1, you get x bar 1, sample 2, x bar 2, sample 3, x bar 3, so on and so forth. You have a bunch of x bars, and you can talk about, excuse me, what would a histogram of the x bars look like? What would the mean of all these x bars look like? And what would the variance of all these x bars look like? Now, a histogram of the x bar, we call that the sampling distribution of x bar. And knowing the sampling distribution of x bar, we'll see when we do confidence intervals, allows us to figure out how good our guess is of mu, how far x bar is from mu, without even knowing mu. It's actually weird, and we'll leave that for when we do confidence intervals. So the sampling distribution of the sample mean just more or less says, what if you do this thought experiment? Sample of size n, you get x bar. Sample of size 2, sample 2 of size n, get x bar. Sample 3 of size n, get x bar, so on and so forth. What would the distribution of these values be? I mean, in a simple sense, what would a histogram of these values look like? Well, we can talk about x bar in many different ways. It turns out that the mean of x bar equals mu, theoretically. Sometimes x bar is higher than the true mean, sometimes it's lower than the true mean. Sometimes you might actually get lucky and x bar equals the true mean, but this says on average x bar equals mu. The second idea is that the variance of x bar is sigma squared over n. The variability of x bar depends on the sample size. And that's sort of an interesting idea. It says more and more data, the less variable x bar will be, which is kind of cool. So the variance of x bar is sigma squared over n. So that's two important ideas right now. We say E of x bar equals mu. On average, x bar equals the population mean. Sometimes it's too high, sometimes it's too low. On average, it equals mu. The variance of x bar is sigma squared over n. The standard deviation of x bar is the square root of that is just sigma over root n. And it's called the standard deviation of x bar. It's also sometimes called the standard error of the mean. It tells me how good my guess is, how good x bar is a guess of mu. I like just calling it the standard deviation of x bar, but it's sigma over root n. Now, there are two ideas. The law of large numbers says that the variance of x bar equals sigma squared over n. Well, as n gets bigger and bigger, sigma squared over n goes to 0. So this more or less says x bar goes to mu as n gets really big, which is what you want to happen. So things that have no variance are constants. They don't vary at all, they're constants. The variance of x bar goes to 0 as n goes to infinity. That means your guess gets closer and closer to the true value mu. Cool. You want that to happen. That actually has a name. It's called the law of large numbers. As n gets large, your guess goes to the true value. Central limit theorem says more. The central limit theorem says that if random samples of size n are drawn from any population, and that's cool, it can be discrete, can be continuous, drawn from anywhere, x bar looks normal. X bar follows a normal distribution centered at the mean mu with standard deviation sigma over root n. Now, if you start with something normal, this is true for any sample size. If you start with something arbitrary, it's true when n is large. In general, we say n is large if n is bigger than 30. There's some weird data sets where it doesn't kick in for a long time, and it's 400 or so. But in general, if n is bigger than 30, we think the central limit theorem kicks in. So what is it saying? It says if you draw samples of size n bigger than or equal to 30 from any population, so here's a population that's not normal looking, then a histogram of x bar follows a bell-shaped curve. Not the original data set, but when we talk about x bar. So it's really cool. If we want to talk about x bar, it doesn't really matter where the data comes from. As long as we know we have a lot of data, we know we're working with a bell-shaped curve. Very powerful result. If you start out with something that is normal, boring as all get out, this thing holds for any sample size because sums of normals are normals. But it's a very important result. It says if n is large, the mean of x bar is mu, the standard deviation of x bar is sigma over root n. So it says you could have an original population that looks like that. That's skewed to the right. That's not normal. Take a histogram, take samples of size 2, form a histogram of x bar. Sort of looks bell-shaped, not great. Samples of size 10, form a histogram of x bar. Sort of looks normal, not great. Samples of size 30, form a histogram of x bar. Guess what? Starting to look really nice and normal. So central limit theorem says that if you start with anything, this is the underlying population distribution, it's not normal. As long as n is bigger than 30, a histogram of x bar will be normal. If you start with something normal, then any sample size will get you a histogram that's normal of x bar. This is a really cool and powerful result. It says no matter what you start with, no matter what the underlying distribution is, as long as you want to work with x bar, and that's the limiting issue here, as long as you want to work with x bar is normally distributed. Now, sometimes you may not want to work with x bar. What if you want to work with the median? Or the variance, or IQR or something? Oh, then you got to do something different. Ideally, the bootstrap that we discussed in class. But if you want to work with x bar, you know x bar is normally distributed. Now, we do a visual demo, and that's our first video, and you should probably watch that first. It's a great applet we go to online, and we go through some examples of this. And the best way to really understand what's happening with the central limit theorem is via a visual demonstration. We can also show you this via simulation. So we're going to use a little simulation in R. Don't get bogged down in the details, understand the high-level ideas that we're trying to show you. So what we're going to do is start with a dice roll and show you what happens when we average more and more dice. So a single dice is discrete, by the way. It only has 6 outcomes. It turns out if you do the math, E of x is 3.5. The standard deviation of a 6 outcome die is 1.71. So if you do the math, you can find that. Now, we're going to use the sample command in R, just to sample rolling from a 6-sided dice. And this just gives us random dice rolls. We're going to roll a die 1,000 times. And we roll a die 1,000 times. We get around 3.5 for the mean. Remember, the true mean is 3.5. That's around the same thing. We're trying to show that E of x bar equals mu. E of x bar equals mu, and that sort of shows it here. And then what was the standard deviation was 1.71, and that's essentially what we're getting empirically from our data set. Histogram just shows you it's only doing 1,000 rolls, so it's not all the same height, but you'd expect them all to be about the same height. We're going to take 2 dice, take the average. Excuse me, because we're interested in x bar. So 2 dice take the average, 2 dice take the average, 2 dice take the average. We're going to do it 10,000 times. The mean's 3.5. The standard deviation, this is the standard deviation of x bar, is 1.2. Where does that come from? Sigma over root n. That's what we're doing over here. So we see it equals to theory. And we start getting something that looks normal. Normal? Well, it doesn't, it's pretty discrete still, but it's looking more and more normal. 1 dice was not. This is the histogram of 1 dice roll, very uniform. 2 dice, starting to look more and more normal. 5 dice take the average. So we roll 5 dice, we take the average. The mean's 3.5 that we expect. The standard deviation of x bar should be sigma over root n, which is 1.71 over the square root of 5. And we show you, hey, more or less equals that there. It's cool. Theory equals what we get empirically. And wow, 5 dice take the average, 5 dice take the average, 5 dice take the average. This histogram looking really normal there. And n equals 5. Quite amazing. There's some R tricks. You can actually do this all in a matrix. Each roll represents 5 rolls of a die, and you can just actually take the average across. So there's some tricks in R to do this actually very, very quickly. And then the apply command will take the mean of each row. So there's some ways to just do this very quickly in R if you care about some R tricks. We're going to do 20 dice. So we're actually going to roll 20 dice at once, shove it into a matrix, do this really quickly. But we see the mean's 3.5, standard deviation is 0.37, so the standard deviation x bar, and we show empirically here is 1.71 over the square root of 20. That's what we're showing you there in the math. It's pretty close. A little bit of a difference, but pretty close to that. And look, 20 dice definitely looks bell-shaped. So the recap is that no matter what you start with, if n is large, and sometimes it happens very quickly. In the dice roll, it started to happen when n equals 2, but the general rule says if n is large, if n is bigger than 30, the distribution of x bar, the histogram of x bar, is normally distributed with mean mu and standard deviation sigma over root n. So again, you start with anything and n's large, you get a normal of x bar. If you start with a normal, boring, sums and normals are normals, you always get a normal at the end. We'll show you an example of this. And this is still a theoretical exercise. There's still a lot of theory here. When we do confidence intervals next, you'll really get an appreciation for the central limit there. So here's the setup. Suppose a population's mean mu and standard deviation sigma equals 3. And that's a big suppose, right? That's telling you all the population values. And when we get the confidence intervals, we don't know that stuff. And we'll show you how to work when you don't know this stuff. But right now we're assume you know the population values. Suppose a random sample of size n equals 36 is selected. So that means n's big. Central limit theorem is going to kick in. What's the probability that the sample mean is between 7.8 and 8.2? So we're asking you this question. What's the probability 7.8 is less than x bar is less than 8.2? That's what we're looking for. Let's ask a different question. What's the probability that a single observation is between 7.8 and 8.2? So what's the difference? Now we're asking 7.8 is less than x is less than 8.2. So how's this different? This is asking x bar. This is asking x. Well, are we told it's normal? No. Are we told it's binomial? No. Are we told it's a t? No. Do we have a probability table for x? No. You can't answer the question. Unless you're explicitly told the distribution for x, you cannot answer this question. You have to be told more about x. However, because n is large, we know central limit theorem kicks in, we can answer this question without any more assumptions. we don't know we don't have to know anything about the underlying distribution of the x because we're answering a question about x bar. Well, we are answering a question about x bar. That's the only limiting thing here. We're not going to talk about x anymore. We're going to talk about x bar. But it's a powerful result. It lets you talk about x bar without making a lot of assumptions about x. So what's the probability x bar is between 7.8 and 8.2? Well, from central limit theorem, and because n's large, we know x bar falls in normal distribution, centered under true mean 8, standard deviation sigma over root n, which turns out to be 0.5. Then the probability x bar is between 7.8 and 8.2 becomes a simple probability calculation that we can do in R, we can do online, we can almost even do by hand. Excuse me. So, unless you're explicitly told the distribution of a random variable x, there's no way to find the probability x is between A and B. However, as long as n is large, the central limit theorem allows you to evaluate probability statements about x bar. This actually is a powerful result, with the caveat that it's a powerful result if you care a lot about x bar, which most people do. It's the simplest thing you can talk about, like what's going on with the mean of my population. So the central limit theorem says without a lot of assumptions, you can answer questions about x bar without having to assume anything about the underlying distribution of x. It's a little bit weird. Go back to see the visual video also. That'll help you out here. And we'll do several examples. We'll do one more video where we do a couple examples. And then when we do confidence intervals, you'll see how it all fits into place and becomes a little bit less of a theoretical idea. Hope this helps. Let me know if you need any additional info. And looking forward to seeing you in class. Thank you.